Welcome to EDU World Space.
Here we're asking the question, what would happen to a small charge that's pushed a small distance up the axis of a thin ring that holds a negative charge? So it's important to realize that the positive charge would be attracted to the ring, and we're going to look at the nature of that attraction. The way we're going to be doing this is we are going to be using the force on the positive charge is the product of the Q times the electric field. And we are going to find the ring electric field with the idea that it's coming from a number of infinitesimal point charges that are inside that ring. And we are putting those point charges all the way around, of course, and adding them all together using an integral of some sort. So those are your source points. And we're going to consider each one creating a small infinitesimal electric field that we're then going to add over. And usually you write that electric field as the electrical constant, which is 1 over 4 pi epsilon naught, times the charge. And usually there's different ways to write this, but I'm going to write this as a linear charge density times a linear differential in length. And I'm writing it hinting that it's going to be an arc length because we're going around the arc. And usually you see a little r unit vector over r squared, but I'm going to write those as a different way. I'm going to use the fact that the unit vector is the vector divided by its magnitude and slightly rewrite that. And the important thing to realize is that r is the difference between your observation position minus your source position. Our observation position is along the x-axis. I'll just show it arbitrarily up there above the ring. And we call the axis x for axis. The source is lying in the YZ plane. So we'll write the coordinates down that way. And we can now write down what r vector is. And we could write the magnitude. Good old Pythagorean theorem with the simplification that the y squared plus the z squared have to add up to the radius squared. Okay, and a couple of other things to verify in this differential. The linear charge density that we're dealing with it's a negative charge minus q divided by the circumference of the ring. And ds is an arc length going around in a circle. And we are assuming only one radius, a very thin ring, with theta going around in the YZ plane, all the way from 0 to 2 pi. Okay, so we can now put all this together. And the first thing I'm going to note is that the only electric field component that should matter is the x component. Why? Because of symmetry. That is, if you look at the source and if it's really uniform, there should be a positive source point, say on the left half of the ring, that identically balances out a source point on the right side. Okay, so we've got to put in all our information. Let's see, the integral over ds r cubed. And then the x component of that vector is just x. And notice I'm putting that outside the integral, that x, because it is not part of the source. It's the observation point component, coordinate. Okay, and we can fancy this up a little bit, put all the other stuff in there. Put in for the charge density. And the x. And our integral, r comes out d theta from 0 to 2 pi. X squared plus r squared to the 3/2. Okay, so notice that that function inside the integral doesn't actually depend on theta, so we can pull that out. And yeah, it's kind of silly. Now we just integrate over theta from 0 to 2 pi. And we have a final EX. Let's see, this whole integral is going to give us 2 pi. And I see that my 2 pi will cancel top to bottom. And a quantity of r will cancel. Well, that's nice and convenient. And we're left with x over x squared plus r squared to the 3/2. Okay, now this is interesting. That component gives the right value whether you're above the ring or below the ring. The sign will switch, or the direction of the E will switch depending on which side. But what's now going to become of interest is that the force on the positive charge looks like minus little q, ke, qx over x squared plus r squared to the 3/2. Okay, now what's interesting about that? Well, I note in particular, if x is much less than the radius, then we can basically ignore the x down in the denominator. And our force looks like then minus q ke q x over r cubed. And notice that this says that the force is going to be proportional to the distance from the center. What we basically have is a Hooke's law type situation. So recall that the force on a mass on a spring goes as force equals minus spring constant times x. Stiffness or spring constant is that K. What that force gives rise to is simple harmonic motion. And we know the frequency is equal to the spring stiffness over m. And if you wanted the period, you could relate the angular frequency to the period of the oscillations. Okay, so with this small approximation, we see that this charge will oscillate like a simple harmonic oscillator, pretty much, with an omega equal to, of course, square root of spring constant over m. And the stiffness constant we can just read off of the quantities in front of x. So the more charge there is on the ring, the stiffer the spring is. The more the small charge is, the stiffer the spring is going to be. And the smaller the radius, the stiffer the spring will be.